Hello everyone from Austria. Today we are talking about geomagnetically induced currents and space weather prediction in Austria. My colleagues are Rachel Bailey and Philipp Schachinger, and my name is Dennis Albert. We are from the Austrian Meteorological Institute and from Graz University of Technology from the Electrical Power Systems department.
So we're currently working on a forecasting approach specific for Austria to try and forecast the GICs in the region from incoming solar wind data. This doesn't specifically forecast dB/dt like many other studies have done, but attempts to directly go to the geoelectric field, because this is what really drives the GICs. The model being trained is an LSTM, which is a kind of recurrent neural network good at handling time series. And the input data for training and testing is 26 years of Omni data, which has been back propagated to L1 to simulate what it would be like in real time. And we're training it on the geoelectric field modeled from geomagnetic variations. So it takes 2 hours of solar wind data at L1 and then outputs the maximum electric field expected after expansion time for Earth. So that should be producing output for a real-time forecast soon. And the output of that will be the GICs calculated from the geoelectric field in both components.
The calculation of GICs starts with the calculation of the geoelectric field. In our case, this is either done by defining electric field scenarios or by using the plane wave method with 1D Earth models and geomagnetic field measurements. From power grid data, we create a power grid model, which leads in combination with the electrical field to driving voltage sources for each substation. In contrast to many other calculation tools, we use nodal analysis to calculate the resulting currents in the grid. Afterwards, we compare our simulations with our own transformer neutral point measurements and investigate the influence of certain parameters on our simulations, for example, the influence of unknown substation grounding resistances. This leads to improved power grid models and higher correlation between simulation and real measurements. With the simulated GICs and detailed transformer models, we calculate the impact in regards of power quality aspects like voltage distortion or additional reactive power demand of transformers.
In order to validate the GIC simulations, we perform GIC measurements at 7 transformer neutral points in the 220 and 380 kV voltage level of the Austrian power grid. The power grid and the equipped substations are depicted here on the left-hand side of the slide. In the upper part of the slide you can see the measurement system and the cabinet installed at a substation right beside the power transformer. On the left-hand side of the slide you can see the measurement electronic, which is accessible from remote via UMTS. In addition to the measurements on-site, we perform power transformer laboratory tests. We have modified 250 kVA power transformers in a way that the low voltage vector group can be changed from outside. This helps us to superimpose DC or low frequency currents on either side of the power transformer. We have developed also a hysteresis measurement setup to capture the hysteresis characteristic, and we have tested that approach in the lab, and currently preparations are ongoing to test this approach in the field at large power transformers. Additionally, we perform power transformer sound level measurements with and without superimposed DC to estimate the DC level in the power transformer and to predict the transformer sound level.